Hello there, everyone, and welcome to a new final project presentation ceremony by our masterclass students. So, for today's session, we have three presentations by three students that have just recently finished their final projects. We are going to be covering topics from manipulation to perception, autonomous navigation. So it's going to be a very complete session. I hope that you can learn a lot from it. And as always, I want to remind that we are always going to have a brief Q&A session after the presentations with each student, talking a little bit about their project. So in case that you have any questions to share with the students about their the projects that they are going to be presenting, so you can share them in the chat, in the YouTube live stream. And we are going to be picking some of them to share with the students. So feel free to share your questions there. And so without further ado, let's get started with the session. And our first student is ByungHoon. So he's already here prepared for his presentation. So let's say hello to him. Hello, Moon.
Hi.
Hello.
Hello, can you hear me?
Yes, we can hear you. We can see you clearly.
Okay. Okay, so can I start now?
Yes, all yours. The audience is all yours.
Okay. Thank you, Alberto. Thank you, everyone for joining this event. I'm BH Moon, and I'm a Korean living in Taiwan. I personally like some robots when I was young. And then finally, I had a good chance to learn take a nice courses in this construct. And then I study very heavily for last more than 8 months, and then finally reached to this point. I'm so glad to have a final presentation today. So I'm going to share my screen from now to show my project. Give me a second. Okay, so I think you can see my screen. So
Yes, we can see
my
it.
name is yeah, good. Thank you, Alberto. So my project name is Manipulator in the Moon's Cafe. So there's a robot, a very simple robot we call robot arm in the cafe. Then he's picking up the coffee from coffee machine and then place on the delivery robots. So I start from March and then finally reached the point 8 months now. Okay, so the objective of this project is to develop the program that achieve following requirement. So you're gonna pick up something and then move somewhere. So for the human beings, very simple things like you can do it very simply. Like you know where is the target, where is the source, and then you pick it up and place somewhere. But however, for the robot, it can be very difficult to explain everything. But however, the genetic process is the same. There's some information and data, and then you know where is the target, where is the source, and then you shoot them to an action. So I'm working in some company, and then we are doing similar job, very similar job in the company. We do the data analysis, and then we analyze and decide something, and then make an action out of the analysis. So the project is to pick up the car from the defined fixed location, and using camera, and we identify where to place, and the location can be changed by because the robot can be moving uh, from time to time, and then we're gonna make some configuration to robot arm to move, avoid obstacles, and I have to create a script to plan and execute the arm trajectory. So this is a motivation why I was working on this project. So when I see this simple robot, I was thinking like it's very simple. There's a lot of motors inside, and then they are moving somewhere, and then they pick up something from somewhere and then move somewhere. But however, when it comes to the realities, I have to think about what the software inside, and then how do we control each motors, and what if the placement location can changes. So eventually, I have no idea how to do it. So that I was looking for where can I learn this. And I finally find out from the construct, and then this site has a very well-defined programs that they train the robotic engineers. So this master courses consist of very nice contents, and then very enough the contents to grow the robot engineer. So to achieve this goal, I have to learn a lot of things, like the simple list of the major item, but below this one, there's a lot of things. So there's a Linux, GitHub, the Python, C++, ULDF. ULDF depends for the robot descriptions and transformation of the coordinates, navigation, manipulations. Also, perception is about how to perceive the outside by robot, and all the kinematics, mathematics inside, control, path planning. So, wow, there's a lot of contents in this the master classes. And I will show you first what the project looked like, so you can decide which curve in this right top image shows. For example, there's a number here, the 1, 2, 3, 4, and then I decide which cup to pick up, and the press this button, start pick and place, and then the robot is doing this job. So that he pick up the cup, and then at this moment, I ask him to put in the number one position. Number one position is top right from this image over here, but in the robot, it may be the top left side. Yeah, there's a place on the right position, right? So that I'm gonna repeat this one for the second cup and then the third cup. And then finally, they can do the final cup like this one. So in this window, the GUI, there is the button to initiate this motion, also the cup selection, the choices, and then some robot information. Because of in this configuration, I was able to control the robot, the delivery robots, the motions also. And also there's a log of the information about the where is the cup, and then what is the field. Maybe the cup is field. I'm sorry, this place is filled or not. So there's all the information is listed up here. And there's two windows which is showing the cup holder positions, and then the other one is interdicting whether this location is filled or not. Okay. And second one is the video is same. However, in this video, I show you that the robot is moving. I slightly change the robot positions. However, this arm can put into right position. That means this camera, the interdictions can still adapt the robot position changes. I can move the robot again like this one. And however, this guy can place the cup on the right positions like this. Okay, so this is the system layer. It looks to be very complex, but I will go over one by one. There's a robot and camera, as you can see from the picture. And then this setup, they publishing a lot of information like the topics and service and actions. And then there's the Alvis, which is the visualization of the robot and the environment. And then this guy can do the execute and then execute the pick and place actions. And there's a perception. Perception meaning using the camera information, we know where's the cup locations and whether this is filled or not. But I have to go through this OpenCV and then the a lot of use the cup detection, the circle detection algorithms, so they can detect the cup size and locations. Also priority. Priority meaning I can decide which cup is more is more the which cup we're going to pick up. So that I can decide depending on location, I can put the priority. And then the couple inspectors, I create the one out of node, which is identify whether this cup is empty or not and filled up. And there's the HTTP server, and then there he's managing these web pages. The web page has the button for service call. When the service is active, the pick and place button can start pickup cycle. There's a the topic publisher, and topic publisher meaning when I press the numbers here, which is the cup number, and then he's sending out this is the cup to select, so that this program is listening to this topic publisher to decide where to put the cups. And there's a log display, and then this is the list of the nodes, and then the node has a lot of information log, and then they pick up this information and then display on the log channel, log panel. And the image, I made a lot of image the topics, and then I pick up the images, pick up to show up these two screens. In the real robot, the barista control does not work because of this. There's no connection. And to connect these two systems, we need a ROS bridge web. They are connecting the ROS to the web server, and then the video is connected and the TF is connected. Also, I also created some other services like a pick and place launcher and a log folder. And this looks very complex, but to run this system, you have to activate the camera system first, and then move with packaging and Albis and perception, and then HTTP server. And the web stack, he's dealing with the web camera, and then the TF publisher, and the web pages, and then web app bring up is the service management. So this is how they are connected between the each nodes. This is a package I have to create to achieve this goal. So there's advanced the perception packages, and then there's a message, the custom messages, and then also Dockers, and then the always the move with the script, which is in charge of pick and place script, and then the my move with pack configuration. And also object detection, meaning using the point cloud, they have to detect where is the surface, the G height of the surface. And then this real advanced perception is for the real robot because they are slightly different because of the real robot situation. And then the simulation, their colors and then the image is slightly different. I'm not going to go over detail, but there's all required packaging for running this program. So you can see it's more than 10 packages required for this one. Also, to visualize the web pages, I need to create the HTML and then the JavaScript, and then I have to connect the loss bridge and the webcam and the table publishers. Okay, so to move the robot, we need some the control, because otherwise the robot can go crazy in the motion. So that I have to put the limit of each joint is by the joint limit YAML file, and you can see each of joint has their limit, so that they cannot move beyond this limit ranges. Otherwise, they can maybe hit other area, and then they can result in the very uncontrolled motions. Also, we can run some the planning scene, so that I can put the boxes so that the RVs already avoided the geometry made by the planning scenes. So there's two the constraint to control the robot in the accurate motions. This is the example of how if we do not control the motion well, as you can see here, pick up and then come back, and you can see become like this one, meaning they don't know the bottoms, so that's why they're hitting the ground because of this is not considered in the robot planning. So that this limit condition, the limit motion is very important. So the other one is the web, the application. Because I have only 30 minutes, I cannot go over everything, but it's 10, 15 minutes. So there's the cycle start by start pick and place, and then this number 1, 2, 3, 4. I can select which the cup position you're gonna select to place, and then there's the kind of video feeding for circle detections. And then there's the panel for logging out all the information about the cup location, the rounds and the circle sizes, and also priorities. Right. So, and also there's another the camera feed for the interdiction for the occupancy detections. Okay, so the coordination system is very important because of this robot arm that they move based on his base link. But however, the camera is watching in the other position, and then they have to talk each other that because of the cup position, we have to describe this I'm sorry, the position by based on the base link. That's why we need to transform between this camera coordination and then the base link coordination. So if you see from the top side, you can see it's a very round shape and then very square. But however, if you see from the camera view point of, this like eclipse point of view. So I have to go through all the transformation, the metrics, and then convert the camera image information to the robot based information. So that this is the C here meaning camera based coordinate, and then the W base is the world frame the coordination. There was one guy who explained this so very well. I follow his the guideline, and this is very detailed about the tape frame. I'm not going to go over detail. And then this is the image processing. So this is the raw images, and you can see the image is not square because we are seeing from some tilted angle. And then I'm converting them into the bird eye view so that it looks like I'm seeing from the very top of the this robot. Um, I mean the delivery robot. So you can see everything square, and then the image of this robot is really round. And then I can find out the real coordination of each locations. And then using these images, I can apply the circle detection algorithms so they can detect circles and then identify whether it is a field or not field. Also, using this you know the tilt corrected images, um, I can define the each of the coordination of the from the base link, and then finally I can show the output of some small size of images like this one. It's cropped from these images. And regarding the G height of this the barista robot, so we can use this program using the point cloud. We can detect surface, and then this value is found by the program. So that I did not use this one in the live the runtime. I just put this value in the hard coded value so that it can have a consistent. Otherwise, sometimes I found this G value is slightly changing for each detections. So I put the hard coded value for my codings. And this is a simulation layout. I'm not going to go detail, but however, the origination is here, and then the robot is far away, and that's why. Okay, I'm just going to skip this one. This is the gripper poses, and then the arm poses. The motion planning, there's a several way to control the motions. We can give them joint value, like here. We can give them the joint value of each joint. Also, we can give them the pose motion. So the meaning this the numbers here is defining the x, y, z, and then the x. Well, I'm sorry. This is the quaternion value of the rotations, and it is telling where's the end point and the effector positions. And the other one is the waypoint. So we can move the robot from one point to the other point by Cartesian motions. And also we can control by predefined position by like this gripper. The open meaning we already defined this open position in the programming, and then we give the command to follow this open position. There's a several way of to planning the motions. So regarding the motions, the Cartesian meaning from one point to the other point, they move in the straight line. So that they pick up the curve from here and they place into target positions. However, you can know that this position is cannot go directly because of their robot is hitting each other. So that I cannot go directly. So that's why I have to the move to the so-called middle stage point first, and then the move to the each point later. So I have to do the two steps motions. Right. So this is the real robot simulation that I recorded for the case maybe system errors happen. So you can see the robot is picking up some air and then placing into the target position. Okay. Now I can do the real demo if the lab is ready. Alberto, is it lab is ready?
Yes, should be ready.
All right. So hold on a second. Oh, what's wrong with my screen? Oh, what's wrong with my screen here?
We can
Okay,
see it properly.
yeah, okay. So there was some, okay, here. Okay, so I need to start from the camera first. Okay, I'll start camera. Yeah, every time I have to start this camera. Let me put this. Okay, he's installing the camera related packages now. Okay. Okay, seems like it's working. Before move it, I have to install some package for web services. So that I prepare the installation program in advance here. So let me install the WebSocket and then the some other packages a little bit. It takes time to install the WebSocket web video server. I found the web video server is not installed as the baseline, so I have to install all the time. Be patient, it's coming soon. So 97% now. So I still have 10 minutes, okay? 10 minutes should be all right. All right, okay. Okay, installing the PyCotonian now. It's almost done. Okay, now I'm going to launch the Move It. Right, Move It is okay. So before the launch Alvis, I have to put some object inside, and already done, and then I will start Alvis. All right, and then I can start let me wait until the Alvis comes up. All right, okay. So let me turn this guy to right directions. Okay, now I'm gonna launch the perceptions. So this package is to recognize the cup holder locations. All right, so he's actually detecting now. Okay, he's detecting the cup locations. There's a 3 cup which is empty, and the 1 cup is filled now. Right, one position is filled. Okay, And then now I have to start the web server. So after web server is ready, web stack, they're actually connecting web between web and then the RS2. So they are sharing the TF and the video, those are the communications. Okay, it's open down. Now let's open the web pages and also open the bridges. Okay, so all right, okay. So now we have the web page open, so that I need to connect between this web page to the road system. Right. Okay. Now we can see the video is comes out of the RS2 and then reach to the web pages. Right. Today he's detecting something else. Okay. Wait a second. So he's detecting 3 cubs. Oh, today is a little bit different. I don't know why. Okay. And then you can see there's a no log because of I did not launch the log services. Let me open the log services. Okay. So this one has all the log and then the topic handling. Yeah. So you can see the log is showing up now. All right. Okay. And then there's a call, and then let's start. Okay, let me show robot, and let's start the pick and place. And the robot is supposed to move. Right. Okay. Oh. Okay. Sometimes I don't know. Sometimes it's not working well. Let me try to move by the script. Whether this is the script problem. Alberto, this is a robot problem. It's not the program issues. You can see the gripper is moving, but robot doesn't move. Can you restart this robot?
Yes. Okay, so let's
Yeah,
try.
please.
Let's try
Yeah,
maybe restarting the controllers. I think
yeah, please.
we have Ricardo
Yeah,
there in the lab who should be able to
right,
do that real quick.
right. Should I start the move it again if you restart?
I would stop the arm parts, the arm related parts. Yeah. So
I'm related. Okay,
yeah,
please.
move it and so on. Yeah.
Right.
Or you can stop
Okay. Let
everything
me use the script first.
and just
Okay.
relaunch it.
Right. And I can start now.
Wait, not yet, not yet. We have to see the gripper like opening and so on, which indicates that the restart has been made. Because through the bring up process, the gripper like opens automatically. So we have to see that.
Right.
Yeah, we can see there. You can see that the gripper it's opening.
Okay.
The
Okay.
light.
Can I test from my Alvis first?
Sure. You can try a
Okay,
movement
let me
there.
let me try from my Alvis. Okay,
Mhm.
so that I'm gonna move to the home positions from here, and I see. Okay, it's moving now.
Yeah.
Okay, right, nice. Okay, so I will the launch from script first, whether it is working or not. Okay, all right. Okay, it's moving now. So let the first cup can be controlled by the script, but I will use a UI for next cup.
Okay.
All right. So right now, without any the selections, the default is number one. So he will put the cup in the number one position here in this the bottom right from the screen, the video screen. yeah. Oh, yeah. All right. Is it
Yeah, it lagged
is
a
correct,
little
right?
bit. It looks like it
Okay,
lagged
there's
a
lag.
little bit.
Okay.
Yeah, yeah.
All right.
The camera just lagged a little
Okay.
bit.
Now the two cup is filled. So
Okay.
let me select maybe number two. Number two is the
So
top right from the video feed. Okay. So
okay.
now I
So
select number two.
let's
Okay,
ask
and then
Ricardo if
the
he can put another cup also. He's doing
right,
so
please.
right now.
All right. All
Yeah.
right. And then I start the pick and place motion by UI.
Hmm.
All right, it's moving now.
So now it's
So
going
he will go
to,
to the
yeah.
right. First go to the middle stage and then move to the final
Hmm.
positions. Right. So the last the position left. The last position is actually number one as a default, right? But
Hmm.
right, okay. But it's like today the light condition is slightly different, and then right then
Hmm. And
okay,
that one usually is the trickiest one, right? Because it's the one which is more far away.
yeah. Okay. Right. So that now I will place on the number one positions. Okay.
Yeah,
It's a video delay, right? It's a video delay.
yeah, yeah. There
All right.
was a bit of lag there. Mhm.
Okay. Oh, maybe it's too far for
Yes.
robot to reach. I think you moved some places, is it?
Yeah, yeah. It could have been moved. The poster.
Yeah, can you have to move a little bit the inside so that robot can reach?
Yes. Let's ask. Let's
Yeah, you
ask
can move.
if we can ask Ricardo to
Yeah,
put back the cup and then move the
yeah,
barista
yeah, yeah.
robot a little closer to the table,
Yeah, closer.
just a
Yeah,
little bit.
because, right. Because of it used to be in the right side, but right now it's the left side of this yellow box, the pink box. So yeah, the, can you slightly move to
Yeah, we can see
okay.
him. Okay.
Oh, all right, right, okay, great, great. That's enough.
Yeah,
That's
that
enough.
should be
Okay,
enough. Yeah, yeah.
right. Okay, so I'll do it again. Right. So this interdiction is happening for every the cycle of the detections,
Hmm.
but the message is coming for every second. But however, the detection is happening for um, every cycle of the programming.
Hmm.
Mm. Oh my God, it didn't pick up, right? So can you place the curve again? Oh,
Yeah, let's. Okay, so it seems that now we can reach. Let's give it another try.
yeah, yeah. Okay. No, no, no. The curve is broken now. The curve is not. Oh, I need help again for putting the right positions.
Okay.
Ricardo, can you help me again one more time?
Yeah, so I think the copy is already there, right?
No, 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 no. This cup is broken. The shape is not the round. Maybe he cannot pick up
Ah,
well.
okay, okay. It's like broken
Okay, yeah,
the cup. Ah, okay.
because of
I
it was
cannot
not
see
in the
it.
right
Yeah, I
position.
cannot see it very
Yeah,
well from here. So if maybe
I can see well.
we can put
Cup is
another
broken.
cup there instead of this
Yeah,
one.
please.
Okay,
Oh,
there we go.
oh, can you? I don't know. The cup is right position. I don't know. I open the gripper very precisely. That's why I don't know they can accommodate any big deviations like this. No, they didn't pick it up. Yeah, Alberto, I made the gripper very precise opening. So if the curve is not in the right position, you cannot pick up.
Yeah, it's strange. So the previous one it was picking it, right? And this one for some reason.
Right, please, in the right position, please.
Is
Right,
that
right, right.
correct?
Okay, it's correct now. It's correct now. Let me try
Okay.
one more time. Yeah.
Yeah, let's see. So unfortunately, it's the camera is like lagging sometimes. So
Yeah, a lot of laggings. But the final position looks okay, but the gripper is very small opening to the right cup size. That's why it cannot accommodate the big deviation from the original, the first picker position. It seems like
okay,
big
there it
picker. Okay.
is. Yeah, now. Okay.
Okay. Right, you can reach now. Okay.
Yeah, now we can reach.
Okay, the summary, the robot is able to pick up the cup from the fixed location and then place at the target positions. And then the perception algorithm is able to detect the cup hole positions and also can judge the occupancy, whether it's filled or not. And the web GUI can communicate to our system very well. That is my conclusion.
Okay, so let's let's give an applause first of all for ByungHoon. All right, so yeah, thanks a lot for the presentation. It's been very interesting and very educative, right? So especially I think the presentation part, it was very well structured, so it was very easy to understand everything properly. So so yeah, then let's go with a bit of Q&A. So let me have a quick look here at the chat to see if anybody has shared any questions. We can see here someone is saying, wow, amazing. So somebody really enjoyed your project there in the audience.
Thanks so much.
Okay, so no questions so far. So in order to give some time for the questions, I'm going to go with mine because I have actually several questions here. So, okay, so for example, the first one, how do you differentiate between having one of the barista holes empty or filled? Do you do that by color or how do you do that exactly?
Okay, so I was supposed to use the point cloud, but you know I have some camera program, right? So that's why I just rely on the images. So as you can see, the cup with field with the cup is more brighter than the cup not field. So I just use the brightness as a indicator. So the
Okay.
brightness darker from some certain limit considered as a field. I mean not field, and then some if the cup is inside is more brighter, right? So, but it can be based on your situation. Maybe actual situation can be different. Maybe different color curves and then different situation, so that I can accommodate any situation, real situation.
Okay. And another one I was interested is because you explained very well that you set some joint limits, right, in your movie
Joint limit, right?
package,
Right.
and I saw that every joint had like different limits set for them. So how did you
Yes,
decide these values for the joint limits?
it's a good question because of I have to go through all by try and error, so that um, I just move manually and see um, the desired ranges, and then I check each values and record down and then set the value one by one. This is all the painful, time-consuming job for me.
Okay, yeah, it's time consuming, but the result is good because the movements generated are pretty optimized, right? So
Yeah, otherwise it become out of control. These values is all the manually found, like these values here. Yeah.
And also, my third one, and I will leave time for others. So my third one is because you also introduced that you are running like a log forwarder node, and so what is that doing? The log
Which
forwarder.
node?
Log
What?
forwarder.
Look for water.
Yeah, the log forwarder. It's right there, like the third one, starting from the bottom. In the list of nodes, in the list of nodes that you shared or packages.
Right. Okay. The web, bring up this one.
No.
Which one?
It's like another one. Maybe it's related to the web page. Yeah. Here it is in the web app bridges. There is pick and place launcher, and the second one is log forwarder.
Look forward. Right. So each perception, they actually are sending out a lot of node warning or like messages. How do you call it? Log out, right? And then they pick up all this log and then send it to the UI. So I have to make this log for the programming.
Okay. So this is basically for showing the logs in your web page, right? Those
This
ones
right.
that
This log.
we were seeing.
Yeah. This log. Log.
Okay.
You can see there's the node name and then there's log information. This is the directly coming from the RS and then come to the web application.
Okay. Thank you. So we have some questions here. Then let's go, for example, with for example, one from Girish, I can see here. So he's asking, why was the kube whole occupancy image showing a split image sometimes? What was going on there? So we saw.
You mean
we saw that, for example, sometimes the in the circle detection row, and it was like moving and detecting like other holes, and what was that noise or?
It seems like the two images is displayed at the same time. So there's more like I don't know, but this is capturing based on this round detection. For example, I'm detecting this big circle of the barista robot, the edges. However, sometimes they can make a mistake and then they're misdetecting other round, and then they're overlapping or they're showing two images at the same time. So I didn't optimize that that much at the time. Yeah. Okay. So if they only detect this one round, it should be okay. But they're detecting another round, another circles, big circles.
Okay, so we have another question here. For example, from Dimitri, he says, "I like the simplicity. So Cartesian used to make correct movements of the robot arm, but locations of the cup holder identified by point cloud and transforms from camera. This is all dynamic." Okay, so a bit of many questions in one. But
already you show that even you move the barista robot locations, they already adapted to the new position, right? This is dynamic. It's not a fixed location. It's a real time update every cycle of the perceptions.
Okay, then I would like to add one more question. So, how do you think this project can be optimized? Your current solution, what do you think could be optimized in order to improve the final product, the final solution?
Okay, so this is really the very limited situation that this robot should be in certain location. Also, the robot has some certain height. So that what I can do is more accommodating various situations, like maybe more wide ranges or maybe different height. And also the other situation, for example, I was detecting the curve by the brightness, but real situation can be different. For example, depending on light conditions. So I have to use the cloud, maybe point cloud, to detect the the pockets. That can be more the future the effort I can make. So, but limited time, I just focus on the images only.
Okay.
There's a lot of things to improve here, actually.
Okay. Yeah. So many things to improve, but still is very good and complete project. So yeah, let's leave it here, I think. So thanks again, ByungHoon. So if you want to say some final words.
Yeah, thank you so much for the teachers, and then especially the Girish. So he helped me a lot, and then also he was very disciplined. The evaluator, so that there's no negotiating at all. So that makes me study more harder, and then also appreciate all the construct, because you provide us a very nice organized training course. Is very nice, and then very structured. So I was able to learn how to make robot from the scratches to the final stages. Thanks so much.
All right. So yeah, thanks again, and yeah, we'll be in touch, ByungHoon. So yeah, talk to you soon.
Yeah, thank you. Thank you very much.
All right, so yeah, we are done with the first final project presentation. Hope you enjoyed it, and yeah, we are going to continue with the next presentation. We are going to stay in the same real robot, which is the manipulator arm with the barista. So it's going to be a similar project, but let's see what are the different approach that this next student has taken for his project. He's Kural. I think he's already here. So yeah, let me ask him to share his screen so that we can see him. Share his camera. Sorry. Hello, Ege. Okay.
Hello.
Let me
Hello.
put you
Can you hear
there.
me?
We can see you. We can see you. Yeah. So yeah, all yours. You can introduce your project.
Yeah. I have a background in control and worked a few years in ROS. So I consider this masterclass a good expansion to my knowledge to ROS too, and work with real robots as well. So this is the final project. I'll go share the screen.
Okay, yeah, we can see your screen.
All right. These are the topics of my presentation today. First, we'll talk about robotics automation in service industry and describe my project. I will continue sharing the keystones of my project. I will also be giving basic information in topics, some for those unfamiliar with. The robotics automation is transforming the service industry, bringing efficiency to everyday tasks, from self-service robots in fast food restaurants to robotic janitors in hotels. Robots are enhancing customer experience while reducing operational costs. We see more intelligent systems every day, taking repetitive or labor-intensive roles. One example is coffee service, like our project. The idea may seem simple, but coffee serving involves several challenges, such as handling cups, pouring liquids, managing different tools with high precision. The robot must accurately detect where to place or pick the cups, recognize objects, and sometimes identify human gestures position in real time. The robot needs to follow logical steps, coordinate multiple actions in success, and do that in safe motion. This project focuses on robotic automation of handling cups between a stationary counter and delivery robot. The manipulation is done using the UR3E 6 degree of freedom robot arm. Systems use vision as guidance using data from the 415 depth camera. Delivery robot must position itself within the view of the camera and within a reachable distance to the arm, one of the limitations. It shouldn't be too far or too close to the coffee counter. The cup to be picked is detected in simulation, but in real lab there is no camera such that, so it is hard-coded value. The cup should be ensured stay upright during the manipulation to not spill. One of the extras, I think, I implemented a recovery strategist in case of planning fails to handle situations where the path is blocked by an object and it is unsafe to do the manipulation. I decided to add such inclusion because in industry, in real applications, usually the robot arm is within an enclosed space and do the manipulation without any obstruct. But in our case, it reaches outside of its safe area, the coffee counter. So it's a good. I thought this is a good opportunity to test and also utilize the behavior trees. I will be explaining that later. The backbone of the project, the manipulation. Manipulation is done using the Movie2 C++ API. Movie2 is widely used for tasks involving arm movement, grasping, and doing it with collision avoidance. I utilized Movie for modeling, kinematic modeling of the robot structure with small group interface. It has a useful tool, Movie Setup Assistant. It's a simple and intuitive usage with little knowledge. There are tutorials as well. To planning, I use selected OMPL planners for generating smooth collision-free trajectories. Constraints-based planning to ensure robots moves within defined limits, like orientation limit to make the cup move upright, and avoid collisions using the camera data. I will be explaining that. And finally, executing plans with inverse kinematic planner plugin. OpenMotion planning library provides wide range of algorithms designed to compute feasible, efficient paths for robotic manipulators. It supports various types of planners based on planning scene and the problem type. The most widely used ones are geometric planners, planned directly in configuration space without simulated physics, and most of them are RRT based, including the ones the Movit uses by default, the RRT Connect. It is among the fastest one of the Movit. There are other types, control-based planners and multi-level planners. Control-based simulates dynamics and control signals. It is useful for robots controlled dynamically. These planners can also work in control-based context if configured accordingly. So also they can operate across different abstraction levels. So there are some other complex options for within the Move It API. My choice of planner was using two of them actually interchangeably. I decided that by trial and error, trying many of them. Bi-directional transition-based RRT is one of my choices. It combines RRT with transition tests that penalize unstable or high-cost paths. It works very good at quickly finding paths in cluttered spaces. The second one, main one actually, the kinematic planning by interior-exterior cell exploration. KPS is designed for systems with complex constraints and limited controllability. That it can handle complex environments better than RRT-based methods. I use KPS for that reason as well. Constraint handling in cluttered environment. I tried many planners, but find more success with this one in my testings with minimal tunings. One weakness I could say of KPS is it can be slower in open spaces compared to greedy planners such as RRT Connects or other RRT methods. KPS doesn't explore randomly; it systematically covers difficult regions and includes constrained spaces. Kinematic solver, as I used LMA, Levenberg-Marquardt kinematics plugin. It calculates the joint angles needed for robot arm for specific end effector pose. It works iteratively to minimize the error between the current states and desired pose, and it requires a valid starting configuration. So to ensure safe manipulation, the robot must relies on representation of its environment known as the planning space. In planning space, objects can be manually edited using the planning scene interface via the Move It API. Objects such as tables, walls, or other previously known objects can be edited. The another method is dynamical, using real-time sensor data like depth images, point clouds, to process it into a Octonet or 3D occupancy map. This is useful for environments where robots' operation space is not enclosed and risk during the manipulation. That's one of the reasons I decided to use. I use both in simulation and real, both static and dynamical methods in simulation and real robot. Combining them helps more robust motions and adaptive manipulation. All right, the perception part. My first method for detecting cup holders using the point cloud data, which is processed with RANSAC and K-means clustering algorithms. RANSAC plane feeding algorithm works iteratively and finds planes to random subsets of 3D points, and then selects the model with most inliers. It is ideal for detecting flat surfaces, and it is robust to noise and outliers. Following that, K-means clustering works, clustering 3D points based on spatial proximity. It is simple, efficient method for grouping data. These two algorithms often used in perception pipelines. RANSAC for detecting geometric features, not necessarily flat surfaces. It can be many things. And K-means for grouping spatial data. The process of detection goes like this. The first point cloud is filtered by region of interest, which is where barista robot is. Then ransack plane fitting applied to, and tray surface is obtained. Thirdly, a second filtering applies to extract points just below the tray surface within a certain radius and distance. It's highly improved my detection results, so it was a good execution in that. K-means clustering then applied to the cup holders, and the cups, the results with small offsets, they are enumbered, and it is used for service calls by numbering them each. The point cloud detections were my only choice in the beginning. It was a good pipeline, but it has limitations. And that I decided to add another method, of circle detection, to complement it. A problem. It's a feature extraction method of OpenCV. It detects circular images. It uses edge detection to find edges in the image. Each pixel votes for possible circle through it, and these votes accumulate X, Y, and radius. The results are circles with high votes. It says shape specific, so it has to be circular, the shape, and it is no training required, such as training a neural network or heavy might be burden to the equipment, the environment. One of the downside is it has to be, parameters has to be fine-tuned according to the application. So that might need retuned each time if lighting conditions change, environmental conditions, or it should be dynamically for the better approach. The steps were simple. Simply, I convert to grayscale, then applied Gaussian Fuller. Then, after some parameter tuning, trial and error, I applied Hopf circles method to extract the circles. And since the robot labs lighting was reliable in most of the time, I didn't need to change these parameters much. So I just tune once and move on. And final step is to convert 2D points using the depth data via back projection method to 3D points. Methods together, both detection. So final step is to fuse together for use as cup holder detection. For the cup holders, I used a simple weighted average method to fuse them. I relied on point cloud data more in the simulation, gazebo simulation, while I added detections about equal in the real-time data. It worked both. It was working fine. I used point cloud detection for cup detection and tray surface detection of the robot, barista robots. I should also remind that the cup detection only for simulation part. there are limitations. One of the I should mention one of the reason I decided to add another detection to complement it. Sometimes there are one time I encountered during the test, the depth image can be partially missing due to physical properties of surface or camera limitations or environment conditions. This was a odd case, not. I use most of time. I decided rely on conditions being perfect, not changing light conditions. So for a different light conditions, I need a more robust algorithm. Maybe a neural network need to be trained more. This can be improved in such real cases, real applications. So the behavior trees. Behavior trees are modern and modular approach to define robot behaviors. They organize robot behaviors in trees-like structure where each node represents a task, condition, or logic. One of the biggest strengths of the behavior tree is our ability to handle fallback strategies. In case of a task should fail, revert, fall back to another node or retry the same node again. In contrast, finite state machines is another approach, a traditional approach where the robot moves between the discrete states. They are straightforward and work well for small well-scoped projects. But as the complexity of the FSM grows, it suffers from called state explosion, where number of states and transitions become hard to handle. Behavior trees are more scalable and modular and can handle fallback strategies. That's why I decided to use it in my project. And also with the familiarity we get in the masterclass, it's a good opportunity to try it. I decided. Okay, this is the my tree we have from the root, the tree behavior tree viewer. It controls the delivery service of the cup. It's sorry. The nodes in the tree are executed from left to right, and it shouldn't be mixed with rows nodes. It's not the same thing. BT nodes are individual programs that decide and execute actions based on the conditions. When the service call is received, it starts with validating the detection first, and then if it is successful, passes to next one, from the left to right. So it is this prepping node makes robot move just above the location of the cup, the picking location, and then approach and robot picks the cup. The place or recover this is a fallback method. The main reason I decided to implement the BT at the first place. What it does, in case if anything fails during this pre-place, by the way, moves the robot arm carrying the cup to a goal location just above the goal location, and this approach puts on the hole. In case something fails in this sequence, the program goes to this putback node. It does when the planning tries to first do the pick and place. In case it fails, it moves back. It moves the cup back to its original location where it is picked. If it is success, it returns to beginning location for getting ready for the next call, service call. Also should mention, if all succeeds, the program goes to this node as well as returning the beginning position. That's how the general flow. As a web app and also desktop app, I used Foxglove. It's a simple modular tool to monitor and debug ROS nodes in real time. It connects via Foxglove bridge, which works together with the ROS bridge server. The bridge acts as a WebSocket client and allows subscribing topics, sending commands, sending service calls, and etc. I use both. I will be using desktop app with my simulation demo and web app with my real demo. But however, due to unfortunate events, I won't be able to send command with web version in the demo. I won't be able to showcase full in action web version because there has been an update which it doesn't work anymore. My sending comments, sending service, it fails basically. So before heading to demo, I want to show my system data flow, the overall. This is the intended setup utilizing Docker, but Docker I will be only using in simulation for Gazebo, and real lab it will be used as this. The Moveit contains the robot configurations and kinematic configurations, and using Moveit to C++ API, I created methods to interact with robot, send commands. Using that method, my delivery sequence is executed. It is controlled by BT, behavior trees. Detection is received depth camera, RGB camera, and it is converted for this to Octomap as entered with Moveit setup to also the detection part. For cup holder detections, I will be using both detections, the fuse detection, but cup and tray, or I will be using only point cloud in detection. Oops. And finally, all data flow with web app or desktop app controlled via the Foxglove and Foxglove bridge through Foxglove bridge. Yes, that's the basic setup. All right, it's time for simulation. I will do a demo in simulation. The Dockers are already created. Both there are Gazebo and manipulation Dockers are ready. I will simply compose up the Dockers. I will be using that desktop app of Foxglove to visualize data. let me prettify a bit. Yes. Right. The robot is not loaded for some reason. The desktop app is connected via the default port. Oh, yeah. It is loaded for now. Also, there is a status feedback telling what the robot will be doing. I will be sending the goal to put the cup, for example, less than 0. It's just telling what it's doing. Unfortunately, I cannot visualize Octomap in Foxglove. There is no such. It is not implemented. So, yeah, that's one of the reasons I'm also using the RVS to visualize. In addition. If something fails. Apparently something failed. I don't have a fallback method since it's a simple step of the picking of the cup. I didn't complicate it too much. I will just restart it quick. And also, I will start the Groot, the live preview. I'll just restart the gazebo again. It sometimes happens the gazebo creation failed the robot. I hope it will work this time. Apparently not. Okay, seems okay now.
I'll go ahead and send. Also forgot show the GRUD. Live. This is the live tree view. The node view. I will send it again to showcase. Spawn another cup. And send, for example, this. It seems it has failure again with move group. Some odd case, it was not happening frequently. This problem. I will go ahead move with the real robot demo. Oops. Alberto, can you hear me?
Yes. We can hear you. So
okay.
we are moving now to the real robot demo, right?
I will be installing the dependency packages in shortly. So
okay.
Then,
Girish was mentioning there in the chat that maybe the robot collided with its own link. I don't know. It looked like the gripper was close to one of the arm links. Okay.
as I said earlier, I won't be able to showcase sending comments via web app of Foxflow due to last minute error, I will say. Something happens on developer side of the Foxflow. I think they changed the thing.
Okay. So we are installing dependencies, right?
Yeah.
Mhm.
Yeah, I use the PCL, also behavior trees and etc. The Foxflow bridge as well, but not for the usage for now. I'm waiting this one to end. While waiting that, I will try the simulation again. I wanted also showcase the fallback mechanism when there is an obstacle in simulation, also as well in the real robot. But yeah, the last problem was not expected. Okay, this one. And
Okay.
it's not completely.
Yeah, the first one, it just takes a bit longer to. So now.
Yeah, that seems a bit slow currently. It failed for some reason. I will restart again.
Okay, it could be something with the controllers. So
Might be. Well, let's try again.
maybe it would be a good idea to restart the ARM controllers.
Yeah, could you restart the controllers?
Yeah, let me.
We'll stop the Xeno as well.
should be good to go. Okay. So
Yeah, the controller is rejecting.
yeah, try again. So stop and restart. Yeah. So what are we getting? Like,
Yeah, it's a controller. Something happening with the controller.
it's now more strange.
I'll just try to build
Yeah, I'm going to.
again. All right, seems good now. So this is the beginning position. I will be sending goals via command line, unfortunately. So it will go to the goal cup holder here. One. Oops, that is too close to wall for me.
So maybe we can try another one.
All right, let's try to.
Okay.
So when it's robot out of the limits, it's too close to wall or far, my program that just reject the goal. It moves to just above the goal.
Okay. So let's see if we can have someone put another cup there.
Yeah.
In the X mark. There is a bit of delay, I think, between what we are talking now and the live so. And the YouTube live. So sometimes it takes some seconds for them to listen, but yeah. So is there some way in which we can maybe test the fallback mechanism, or?
Sorry?
Is there some way in which we can test the fallback mechanism that you implemented?
You mean the BT logic?
Yes.
Yes.
Because you mentioned
if
that
you have an object to block the cup holder, I will be sending. For example, I will send to the 0.
Okay, and when should we put the object?
After it starts moving, starts the service.
So
you should put an object not too big, like we can
box
test
or something.
Yeah, it might be a flat or like a box or something.
Okay, and before the arm gets the cube, or right after, or it doesn't matter?
It doesn't matter really. Yeah.
Okay.
The only thing is it has to be seen with the camera, so to Octomap to generate
Okay. So I don't know if someone there can grab a small box to block the hole. It's going to be which one? Number 0 in your
number 0.
Okay.
The corners to the out of the coffee table.
Let's see if we can see someone there. I can see some movement. Yeah, we have there Ricardo. I think that's. What do you think about that? It's okay or too small?
That might be too small.
Okay, so maybe something a bit bigger, like.
Yeah. Or like a flat object like cardboard might do as well. While you are there, could you move the robot away from the wall, please?
What about the object? Does it look?
Yeah, it might block, but not sure. It might be still small because it's the same as cup. Yeah, I can try, but that hole is too close to the wall. So yeah, that's enough. Yeah. So let's wait a bit. Optomap to clear. He recognized the collision.
I mean, it's being detected by the.
Yeah, it is currently blocking the hole, so that's why there's no detection there. It has to be after.
Yeah. So after,
Yeah.
yeah.
I can just do that later. I can show that in simulation as well.
Yeah.
Not constructed. I'll just send to goal, but the Octomap didn't replenish the collision here. Let's send it anyway to 0. Yeah, that is not reachable.
Which one? Are you trying now?
Now it is too far, the outermost one. I will send it to 1 now.
Okay.
The Octomap doesn't clear it here. I hope it will be working in the while robot playing. Yeah, I think its problem about Octomap is not cleared for some reason. It doesn't replenish. It took too much time. Yeah, it went back to the original pose. Could you remove the cup from the robot so I can try again?
Which one?
The cup is currently attached to robot. Okay. Yeah, that's the fallback mechanism activated there.
Okay.
So it's no need. But this is concerning. Octomap didn't clear it here. Can you see the screen?
Yes.
I will start again.
Yeah, so let's try to do a test again for the fallback, okay? And then, yeah, so we will, because we have like 5 minutes left, so.
All right.
Let's try that. So, yeah, now it's going for the cop, and then now it should be a good moment to block it, right? For example?
Yeah, for the number 3
Yeah.
here.
Let's see if
corner.
Ricardo can block the correct one, or...
No,
Okay.
that
Okay.
was the other one. What it would be happen? It would try to plan a motion. When it fails, it should be back to the original. I can showcase in simulation if we have the time. How much do we have?
Yeah. So I think we have to finish it here. Yeah, because already.
All right.
Mm-hmm.
All right then.
Okay.
Oh, my session ended anyway.
Yeah. That's why also, because the real lab session is going to end. So yeah,
I will wrap up. Further improvements, the project would be an additional camera for detecting cup instead of hard coding the value, similar to simulation as well. And also a camera with ROS overlooking the whole setup to enable Octomap for the whole area instead of just watching the robot from top down. Mm-hmm. That would for better collision aware planning. So one of the challenges of the project was determining the transform between the camera link and to robot. We need to publish that statically. So a rigid camera with the known distance would speed up this project a lot. One of the limitations of my planning approach with also constraint planning was barista robot, the delivery robot, must distance within the limits to the robot arm within certain away, like 30 centimeters and not far than 50 centimeters. It's like a limited area of robot. So, any questions?
Okay, so yeah, questions time. Thanks for your presentation, Ege. So let's go with some questions. So now it's the moment. In case that you want to share your questions, write them down in the chat. I will start by mine, for example, in order to give some time. So yeah, then for example, so you started explaining at the beginning about different planners, right? And then in the end, you, from what I understand, you are using 2 different planners, right? So
yeah.
2 questions. First one, you said, I think that you said that you did a bit of trial and test, but how did you decide exactly which one to go for? It was just by trying multiple times and seeing which one performed better. And second also, so how do you decide and how do you decide when to switch from one planner to another? It's for some specific part of the movement you use one, and for another part of the movement you use the other one, or how is that managed?
That was again, as I said, it was a trial. But in general approach, I used bi-directional RRT, transition-based RRT for unconstrained motions, like without orientation constraint, where there is no need to cup stay upright, or there is no cup picked. It's just for I use bidirectional RRT for simple motions, like move down, move up, that kind of, or Cartesian motions. And I used KPs for more constrained motions. And as you remember, the robot moves from the picking place right over the barista robot. It's a long distance with obstacles in between. So I decided it needed a more advanced planners. I of course tried many other ones, including the default one of Move It. The KPS worked best, as I will say. Also, I didn't need to tune the parameters much. That was one of the good things about it. Maybe if I would tune better parameters for other ones, it might work best. But this was my approach in general.
And you are switching them between the
I am switching, right? In between. Yeah. For example, when robot starts moving from starting position and until the cup is placed, cup is picked. The first part, actually, I would say this one, and the more complex motion, I used KPs. Yeah, in summary.
Okay. And another question also that I have. So, for example, I noticed that in your case, when the robot grabs the cup, right? It takes like a long time before it starts the next motion. I assume that might be because of or I think that might be related to the planner that you are using, that it takes more time to generate the path. But I would like to ask you about that. So have you noticed it like larger times, like several seconds in these planners in order to output, to provide you with a valid plan? Or there is another reason why there is like several seconds that the robot is stopped there, like without actually going to the barista robot? It looks like if it's a stop, but I don't know if maybe there it's thinking, and because you are using a more complex planner, it takes longer. So
after picking the cup, it stays a while there. That's sometimes happen due to robot states not updated fast, or the Cartesian planning failed. Might happen that part. But after that, I mean, moving back to pre-pick position, just hovering the pick, that's long planning, the kinematic planning with KPs comes into play. And that takes time sometimes, depending on the planning scene. If it's cluttered too much, it might take a while. Or for sometimes there are delay in the placing part as well. That happens when it tries several times to place. It tries to plan. When it fails, it tries a little bit above. It is like tries a few more times after it decided this is a failure. So it is, is how that works in the current version.
Okay. So we have a question here, for example, from Girish, which might come in handy for your case. So, for example, he says, well, the first question would be, why did you decide to go for Foxglove in this case? And what advantage do you think Foxglove provides in contrast to regular applications like RVs, RQT graphical interfaces, or even creating your own web application?
One thing will say it's apart from aesthetics, is a modern approach and adjustable layout as well. It has an interface. You can load your own raw specs or other kind of data, and you can visualize with that. As far as I know, I haven't tried visualizing a bag using that, but that might be an advantage. Also, sending commands is one of the biggest ones as well. Sending service commands. It has no action commands implement action interface yet. You can send action commands, but there's a service interface. Although I couldn't showcase it. I wish I could. It was working until my previous few weeks ago, I would say. My last previous try. Yes, that's how it is.
Okay, Ege, then yeah. So let's leave it here. So thanks again for your presentation, and yeah. So we are going to be talking in the next days. All right. So yeah. Bye bye.
Bye bye.
Okay, then yeah. So let's move on with the third and final presentation of today. So we are going to be switching the scenario for this third presentation. We are going to be moving to our warehouse environment, and we are going to be doing having a look at a project which is more focused on navigation, but also on doing perception by different means, not using a camera. But yeah, so without further ado, I think we have already here Andreas. If you could turn on your camera so that we can see you, Andreas.
Hello.
Let me see if we can have you here. Okay, let me put you here. There we go. We can see you. Okay, so yeah, Andreas is ready, so the audience is yours. You can introduce your project.
So let me share my screen first. So can you see my screen?
It's loading. Yes, there we go.
All right, it's okay now?
Yes, we can see it.
So hello everyone, my name is Andreas, and I am a student from the Masterclass, just like the previous presenters. I started in March 2025, but the topic of this presentation is a bit different than the previous two presenters. I had to program basically a differential drive robot, RB1, for warehouse autonomy using the ROS2 navigation stack and LiDAR perception. So this project was split into two main tasks. The first task was to make the robot safely perform reliable navigation inside the warehouse environment. And the second task was to detect a pickup shelf from anywhere within the warehouse environment using the robot's LiDAR sensor. Finally, the goal of this project was to combine these two tasks to find, attach, and deliver the shelf to a predefined pose. In the video, you can see how the robot should perform in order to achieve its goal. So to perform navigation within the warehouse, I chose to use the ROS2 navigation stack, which provides perception, path planning, control, localization, visualization, and much more to build a highly reliable autonomous system. To do that, first I had to create a map of the warehouse environment. This was done only once by using the cartographer ROS, which is a SLAM library. In the video, you can see how the map was built by manually moving the robot around the room using the joystick until all the details were shown in the RVs. After building the map file was saved and passed into the map server as the base for localization. Next, to localize the robot, I used the AMCL, which is a probabilistic localization system in ROS2 that estimates a robot's pose using a known map and the LiDAR sensor. On the video shown to the right, you can see how the pose of the robot in RVs corresponds to the actual pose of the real robot inside the warehouse. So finally, to achieve navigation, I initiated 4 servers. These were the planner server, which computes a global path for the robot on a static map, the controller server for local trajectory tracking, the recovery server, which was used to unblock the robot when localization was unreliable, and the behavior tree navigator to orchestrate the whole task. Some important parameters that I had to tune for these servers were the robot's footprint, the inflation radius of both the global and local cost maps, the speed and acceleration limits of the robot during navigation, and the goal tolerances to be as accurate as possible. The ROS2 navigation was managed by the lifecycle manager that could be used to start, stop, pause, resume, and reset the navigation stack in a safe deterministic order. Now, moving on to the second part of the project, which was to detect the shelf. In this task, I used the robot's LiDAR sensor to find the shelf at any pose inside the warehouse. For that, I created a ROS2 action, which relies on 2 cues: the shelf's 4 vertical legs and the 2 reflective plates placed at the front face of the 2 front legs. It runs in 2 modes: A, an intensity-driven front leg pairing, and B, a geometry fallback that finds the 2 parallel pairs in an orthogonal offset between the front and back legs. When the detection is stable, it publishes a card goal and 2 standoff frames on each side of the shelf. This figure shows how the position of each leg was calculated with basic trigonometry using information from the laser scan topics such as the range, angle, and intensity of each emitted ray. This search type was used to find the shelf's position and orientation at the case where the robot was facing the front of the shelf. For the second search type, where the robot could no longer see the front highly reflective plates of the shelf, I used all of the information possible to detect the shelf, which was all of its 4 legs. Using similar calculations, I was able to detect the shelf from its sides and its back. After successful detection, a total of 3 transformation frames are published to approach the shelf. To keep detections clean, I applied 4 simple filters. First, each leg needs to support at least 2 points in a small clustering radius. Second, for the front legs, I used an adaptive intensity threshold. Third, I gave the geometry for the front leg separation and the back to front offset distance to be in their expected range. And finally, I require 2 consecutive stable frames within a tolerance of 5 centimeters. To automate the search task, I developed the following ROS2 node, which initiated a search process. In this process, the robot navigates successively at each point shown in the picture and calls the ROS2 search action server to perform searching. If the shelf is found at any of the waypoints, the search process stops and returns a success message. Some of the limitations of this project were that no matter what I did, I could never detect the back side of the shelf because there were no vertical legs on its rear side. So the robot could crash during attaching or generally during navigation around the back side of the shelf. Also, I could never verify if the attaching process was successful using the LiDAR sensor because its field of view is only at 270 degrees. So to summarize, the behavior flow for the whole task is to initially perform the search process to find the shelf. After successfully detecting the shelf, the robot publishes and navigates to the nearest shelf standoff frame and executes the final approach using the navigation stack. Once the robot is underneath the shelf, it raises its elevator to attach to the shelf and changes its footprint to match the dimensions of the shelf. Finally, the robot moves to a selected goal, releases the shelf, and navigates to its home position. To manage the entire operation, I developed a web-based interface that allows me to start the localization and navigation servers and run the processes needed to complete a full task either automatically or step by step. What I will further improve in this project is to have a bit more time to adjust the navigation and detection parameters for the robot to perform a more reliable task completion. So Alberto, my presentation is now finished, and I will now proceed to show you a live demonstration for the real robot performing the full task operation. So let me share my screen again.
Okay.
Wait a minute.
It's
Can you see my
coming.
screen?
Yeah. Okay.
Okay. Okay. So now connect to the robot. Let's wait a little bit. So I am connected. Let me check something first. All right. Very good. So I will now connect to the web page. So let me find the commands. Is the okay. And
Okay.
very good. And I am connected to a robot. Very good. So okay. Check just to be sure. Nice. So and now I will start the localization server.
Okay.
So we can see the map here in the web page. We can see the 3 waypoints, A, B, and C. So currently the shelf is at point A in the map. And what I will do now, I will try and move the shelf from point A to point B. So let me wait for Arvis to start. Very good. Excellent. So now I will attempt to perform the whole process by moving the shelf from point A to point B. So we can see now the robot will move to the search, the first search waypoint. So it's right here, and we attempt to search for the shelf. It found the shelf already, so it's moving to the nearest stand of frame to perform attaching. We can see here also. It's moving towards the shelf to attach. Very good. It's attaching now. And it will now move the shelf towards point B. It will now detach, change its footprint again to its initial footprint, which is the radius of the robot. And it will now move to its home location again. So as you saw, the robot didn't know where the initial location of the location of the shelf were inside the map, and it successfully moved the shelf to point B, where I selected from the web user interface. So now I will attempt something different. I will attempt something different. I will attach to the shelf again.
So to
And I will
attach,
try-
you clicked on
sorry.
attach.
Sorry, I cannot hear you.
To attach now, you clicked
Yes.
directly on attach, or
I'm only attaching now to the shelf. I will not perform a full task operation. I will only attach now, and I will move manually the shelf to a random point in the map. And I will perform again the same task to see if, so what is happening now? Let's see. Oops. Oh. No, sometimes this happens. Let me try one more time. This happens because I have set the tolerances for the navigation to be too tight. So sometimes it fails to attach. So it's now searching again for the shelf. The robot does not assume any previous position of the shelf. It always searches for it. So it will now move and attach towards the shelf. Very good. So I will try now and manually move the shelf to a point inside the warehouse using the joystick. So what I will do, I will basically try and attach from the back side of the shelf now. So let's see. All right. And I will move the robot to the search waypoint now. I only do this because I have mentioned in the presentation that the backside of the shelf is undetectable. Otherwise, I would just enter a navigation command and navigate towards the search waypoints. So it might crash, the robot might crash only from the backside of the shelf, only from the backside. So I will attempt now to attach again to the shelf and bring it to the waypoint B at the warehouse. So let's see if the robot finds the shelf. As you can see here, the robot does not know where the shelf is. It thinks that it's still in the position B, so it will now search for the shelf. Let's see. It found the shelf. It's moving to the stand of frame, and now it will attempt to attach to the shelf. Excellent. See, very good. Yes. So it's successfully attached to the shelf, and now it's going to move the shelf to the B position on the warehouse, at the warehouse. Now it's going to detach and move again to the home position. So Alberto, this was my demonstration. If you want, you can tell me if you want to try something else. Or we can move on to the questions.
Okay, so okay, then for example, so the searching sequence, how it goes more or less.
The searching sequence starts basically by moving the robot to a search waypoint.
area, yeah.
I've shown you previously some waypoints in the map. It moves towards the first waypoint. If it doesn't, it executes it calls the ROS to action, which is searching for the shelf. If it does not find the shelf from the first waypoint, it moves on to the next waypoint, and it moves along all the waypoints in order to find the shelf. If it finds the shelf in any of these waypoints, it's going to stop and move towards the shelf. So that's how it works.
Okay. So maybe we can try putting the shelf like near the charger zone. That should make it go through several waypoints, right? I don't know if maybe some Ricardo is around there and he can move it. So
I think I will do that already using the robot. So
okay, it's fine. Yeah. As you have the website and you can move it easily, so this way. We have Ricardo there. So okay, yeah. Then let's make him move it there near the charger.
Okay, we'll see now.
Yeah, with the reflectors to put it a bit easier. Let's leave it around there. Let's see.
So it found the shelf already. It's going to move towards it now. Let's see what's going to happen. And now it's attaching. Excellent. So it will now basically attach to the shelf and move the shelf to C location, where you can see here in the map. Because I selected that from previously, basically. So let's see what's going to happen. All right. No. Okay. Okay. So that was my demonstration. Again, if you want to try something else, Alberto, you can tell me.
Okay. Yeah, no, I think the demo is good enough already. So we can dedicate some time to do some questions and try to learn a little bit more. So then thanks for your presentation, Andreas. And so for the audience, please share your questions. I see somebody has been already sharing some. So let me have a look right now to see the questions that we have in the chat. Girish is saying perfect approach to attach the shelf. Nice.
Thank you.
Okay. Dimitri, for example, is asking, does it use Navigator? And if yes, at which steps of the project? By Navigator, I suppose he refers to the Navigator API?
Yes. So I use Navigator almost everywhere in my project. So from going to the search waypoints, to navigating towards the shelf, to attaching to the shelf, and bringing it anywhere within the warehouse. I use Navigator everywhere for my project. Yes.
Okay.
So for the Navigator, I set the tolerances to be too tight because, as you can see, the shelf has a small, very small space to make the robot navigate inside the shelf. So it was very difficult to make such adjustments in the Navigator to make the robot move inside the shelf. So it took me a bit of time to adjust these parameters for the Navigator, but in the end, it was successful.
Okay. So yeah, I saw another question, but I cannot see it now. But anyways, it was a good question. It was one that I had noted down also. So for I mean, for the frontal approach, let's say, it seems clear that you were using the intensities, right? For the reflectors.
Yes.
But for detecting it from the back, what approach did you use there?
So for the reflectors, for the first search type that I used the reflectors. I use basically the intensity that I am receiving from the laser scan topic to find the shelf, and also the separation distance between the two front legs. So the separation distance between the two front legs is about let me think, it's about 0.6 meters. So I get that distance basically to accept only my algorithm. I get that distance from my algorithm to accept only to find basically only that distance, to accept only that distance. That's why firstly you saw that the robot did not detect the charging station, but the shelf to go to attach to. So for to approach the back of the shelf, I used all of the 4 legs of the shelf. So I used the separation between the 2 front legs. The separation between the 2 front legs and the two back legs is the same. So I used the separation between the front legs and the back legs. So if you can see again my screen now, I will show you what I mean. So if I move the robots, let me use this one. You can see in RVs, you can see the 4 points here. So that's what I used. So the distance between these 2 front legs and these 2 back legs is the same. It's a rectangle. So it's 0.6 meters. So the distance between the 2 front legs and the 2 back legs is about 0.16 centimeters. So I get that distance to find the back side of the shelf. So that's what I do.
Okay. So we are getting more questions here. Let's see. So has the robot ever gone off localization? Do you have a mechanism to get it back to proper localization fix? And also, I want to add, so the initial localization, how can you quickly go over that also? So are you using global localization or?
No. I have actually tried to use global localization, but for some reason it used to fail always, because if I started to do localization in a position other than the initial position where you can see the robot right now, the localization system fails to localize the robot correctly inside the warehouse. It thinks that basically one wall is the right wall is to the back, and I think that happens basically because the room is symmetrical basically, and the localization system fails to localize the robot correctly inside the warehouse. So I use the initial pose to localize the robot inside the warehouse.
Okay. And one last question from me, because for example, in the first attachments, we saw that the robot did them pretty well, right?
Mm-hmm.
The last one was a bit more messy in the sense that it didn't enter it perfectly inside the shelf. So why do you think can be the difference between that one and the others?
So the reason I believe that this happens is because, as I have mentioned in my presentation, I just had to maybe improve just a little bit the navigation parameters for the navigation stack. So that's why it happens. If the navigation stack does not have the appropriate parameters to be tight enough, basically, to make the robot perform reliable navigation, it sometimes does not perform always the same. It performs differently between operations. And because I did put what you saw, it was because the robot tried to achieve the goal location at C position within a tolerance of 5 centimeters, which is pretty low, while having the shelf attached. So that's why this happened.
Okay. All right. Yeah, Andreas. So I think we can leave it here then. So
Thank you.
Yeah, thanks again for the presentation. We are going to be in contact in the following days, and if you want to say some last words, now it's the time.
So I want to basically thank Ricardo, my instructor, for guiding me through the whole masterclass journey that I had. And I want to also thank Girish for helping me for evaluating my projects and helping me when I was stuck. He always helped me with any issues that I had. And also I want to thank you, Alberto, for this last month for helping me with any issues I had with the robots. So thank you very much.
All right. So thanks to you for being here with us in the masterclass in this robotics learning journey. So thanks, Andreas. We will be in touch. And so with this presentation, we have reached the end of today's ceremony. We've had 3 student final project presentations. I hope that you enjoyed them all, that you have been able to learn a little bit from each one of them. And so as always, we are going to keep doing these ceremonies and showcasing more student projects as they are finishing our masterclass. So stay tuned for next ceremonies. And hope you've had a good time. And until the next one, as always, keep pushing your ROS learning. Bye-bye.